Here's the solutions to problems 26 and 27 on your energy review paper. Number 26, an 8-kilogram stone is at rest on a spring. A, the spring is compressed 10 centimeters by the stone. What is the spring constant? B, the stone is pushed down an additional 30 centimeters and released. What is the elastic potential energy of the compressed spring just before that release? C, what is the change in gravitational potential energy of the stone when the stone moves from the release point to its maximum height? What is that maximum height measured? From the release point? So let's start with A. This is not an energy part of the problem. We just need to find the spring constant. We know that an 8-kilogram stone is set on the spring, so the force of gravity is pushing down. The spring is pushing up, so the force of the spring equals the force of gravity because it's not accelerating when it's just sitting there on the spring very nicely. The force exerted on a spring is equal to K times X, the spring constant times how much the spring was squished. Force of gravity is mass times 9.8. Solving for K, we just have to divide the amount the spring was squished, the X, the distance that it was compressed, over to the right side and plug in our numbers. We get 8 kilograms times 9.8 meters per second squared divided by 0.1 meter. So we get a K value of 784 newtons per meter. That's how much force it takes to compress the spring 1 meter. Now let's take a look at part B. The stone is pushed down an additional 30 centimeters and released. What is the elastic potential energy of the compressed spring? We just have to plug into our equation for potential energy of a spring, 1/2 kx squared. The 1/2 is easy enough. The K we just solved for, 784 newtons per meter, and the amount the spring is compressed is 0.3. Some people might say, wait a second, what about that initial 10? It already was compressed 10, and was it compressed an additional 30? Wouldn't it be a 40 here? Would it be 40 centimeters or 0.4 meters? The answer is no. It was in equilibrium at 10 centimeters squished, so there it had no potential energy because it wasn't going to make anything move. It was just sitting there very happily. When you squish it extra, that's when it had the ability to bounce back and throw the stone up into the air. That extra amount is what matters, and that's the 30 centimeters or 0.3 meters. Plugging that into our calculator, we get a spring potential energy of 35.28 joules. Letter C. What is the change in gravitational potential energy of the stone as it moves from the release point to the maximum height? All of the energy is conserved, so that means all the spring energy turns into gravitational energy as it goes from the release to its maximum height, and that would be 35.28 joules. D, what is the maximum height measured from where it was? Well, we know what the potential energy is because we just solved for it. It's the 35.28 joules. That equals mgh, so I'm just going to divide by m times g. So I get, when I plug in my numbers, 35.28 joules divided by 8 kilograms times 9.8 meters per second squared, and I get a height of 0.45 meters. Number 27. A skier starts down a hill with an initial velocity of 1.5 meters per second. He starts at a height of 20 meters above the end of a ski jump ramp as shown. As the skier leaves the ramp, his velocity makes an angle of 28 degrees above the horizontal. All of this is provided on a picture on your review paper. How far will the skier be from the jump when he lands, assuming the ground is the same height as the jump? We're assuming no friction on the ramp and no air resistance. So we're going to do a conservation of energy problem first, figure out how fast he's moving when he flies off of the ramp, and then we're going to do a little projectile motion because at that point he becomes a projectile and we need to figure out where he's going to land. So to start, initially he's got some potential energy because he's on the top of a very large hill, and he's got kinetic energy because it says he's moving with an initial speed of 1.5 meters per second. When he's about to take off, he's got no potential energy because he's as low as he's going to get. He's at ground level. But he will have kinetic energy because he's definitely going to be moving when he becomes a projectile. Rewriting the equation without the potential energy gives me PE1 plus KE1 equals KE2. Expanding each one of those for what they are, potential energy is mgh, kinetic energy is 1/2 m initial speed squared, and the other side for KE2 is 1/2 m final speed squared. There's an m in every term, so they cancel out, giving me GH plus 1/2 initial speed squared equals 1/2 final speed squared. Solving for the final speed, I just have to divide by my 1/2 or multiply by 2 and take the square root. Plugging in my numbers, I get the square root of 2 times 9.8 meters per second squared times 20 meters plus 1.5 meters per second. Don't forget to square it. All under the square root gives me 19.86 meters per second for his speed as he becomes a projectile. Now we have to do an old projectile problem. In the x direction, the d, how far away he's going to be, is the question mark. That's what I want to know. The velocity in the x direction is the adjacent part of the triangle. That would be the cosine of 28 times the speed that he has when he flies off of the ramp, which is 19.86. We just solved for that. In the y direction, he's going to land right back on the ground, right where he started. So that's a 0 meters for his displacement. Initial speed is going to be the opposite side of our right triangle of velocity, and that's going to be the sine of 28 degrees times 19.86 meters per second. We don't know what final velocity is, nor do we care, and the acceleration is negative 9.8 meters per second squared. When I plug into my d equals v naught t plus 1/2 at squared equation, I should get a time of 1.9 seconds. That would be a quadratic. Be aware that this d is 0. So it actually does not have to, you don't have to use the quadratic formula. Because the d is 0, you can just subtract your 1/2 at squared over to the other side and divide both sides by time, and you'll be good to go. You won't have a time in this term anymore, and this will only have one time. So you can do the algebra a little bit easier, but you should get a time of 1.9 seconds. Once you do that, you can go right back to the x. D equals v times t. We know what the v is because you can just plug this into your calculator, and we just solve for the time of 1.9 seconds, and that's going to give you a distance of 33.3 meters.